2, 1.
Go.
Welcome, everybody. Today we are very excited to have Jonghoon Choi present their talk, Continual Learning in Practical Scenarios. Jonghoon is a faculty member at Yonsei University, and we are very excited to hear your talk today. My understanding is this talk is going to cover several of your recent and exciting works in continual learning, so this will be an extra informative presentation. So I guess without further ado, go ahead and take it away.
Yeah, thank you, James. Yeah, hello, everyone. My name is Jonghyun, and I'm going to talk about some of my recent work on continual learning in practical scenarios. Okay, so before getting into the details, let me briefly recap. You probably heard this setup like over and over again, but I'm just trying to recap and just remind you what is the class incremental learning, specifically amongst the continual learning, many continual learning different setups. So the class incremental learning is an instance of a continual learning, and the setup is allowing the classes added incrementally. And sometimes it is batch-wise manner. I will try to address this. And most of the class incremental learning setup is assuming that the classes are added batch-wise manner. So in a group of classes are forming a task. And it suffers more from the catastrophic forgetting. Even though the catastrophic forgetting is there while you're using the neural network to train some classifiers, but in the class incremental learning or the continual learning in general, you will suffer more from the catastrophic forgetting and also suffer from the resistance to learning a new knowledge that is called plasticity and stability dilemma, right? And the class incremental learning is assuming that the classes or the task are given in a sequential manner, in a streamed manner, so not given in advance in all data, because it's kind of unrealistic to assume that all of the data is available when you're learning a classifier in advance, right? So the classifiers will be updated incremental manner, in an incremental manner by the given streamed data. So the first data is given the first time, and it contains the classes between 0 and 1 to 10, and also the second task is given, and that contains the class of 11 to 20, and blah 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 blah. So once the new data comes, then you are supposed to update your model incrementally instead of training it from the scratch again. That's the class incremental learning. So to tackle this problem, there are many different ways to do it, and there are some papers to survey these continual learning or class incremental learning methods. So I excerpt one figure. I forgot to cite here. Sorry about that. Excerpt this figure from an archive paper to classify some of the recent continual learning methods by classifying them by the replay method, regularization-based method, or the parameter isolation methods. So the replay method is basically try to replay the previous task's samples. So by sampling some of the few of the previous task samples and just try to use it as a kind of proxy information for the task, past task. So the replay method has the rehearsal and pseudo rehearsal and constrained methods. And the regularization method is basically try to constrain your learned parameters not to be too much strayed from the previously learned parameters. So we try to move it pretty smoothly for the new task so that you're minimizing the forgetting of the previously learned knowledge. And the parameter isolation method is try to keep the previously learned parameters in some way, like fixed network is using the fixed size network so that you're keeping some part of the parameters of the fixed network and updating some of the other parts. The dynamic architecture is keeping the previously learned parameters and add more parameters for the new task, and then using this extended or dynamically extended architecture to do the incremental learning task. So that's the parameter isolation method. And many of the state-of-the-art method is relying on the replay method, I mean, arguably. And specifically, rehearsal method is just try to sample some of the few past samples in a small memory called episodic memory, and try to use this sample stored in the episodic memory when the new task comes, and augment them and try to update the new update the already trained network. And that's a rehearsal method. And the pseudo rehearsal is try to keep some information for the previous data, and then try to rehearse by generating the previous samples. And the constraint method is try to use the previously learned, try to use the previously used samples in the past task, and by the constraining the usage of the previously used data for learning the new task. So these are the replay method, and I'm specifically focused on the rehearsal method because this is very simple and it's intuitive, and also working pretty practically very well. So in trendy setup in continual learning, I mean, aside from the replay method and the rehearsal method, we have to discuss about the setups in continual learnings, because the setups, I try to argue that the current setup in continual learning that we are using every day is kind of artificial. So we have to break the assumptions to make the continual learning setup more realistic. So here, this is the online sample that we can observe in a real world scenario. So as time goes by, the samples are coming in, and the colors are indicating the classes that the samples belong to. So the online samples are coming in this streamed manner, and they are belong to many different classes. But when we are using this continual learning setup, like we are showing here, this data 1, which is the first task, is consisting of the class 1 to 10, right? Which is assuming that these samples are given in this nice manner in a disjoint subset, right? So here we assume that, okay, this is a task I plus 2, and this is task I plus 1. So here the time goes by in this direction. So you're seeing these samples one by one, okay? So at the task I, the ith time, you're seeing this purple and red samples, which means that you're looking at the samples that belongs to the purple class and the red class only. And at the time I plus 1, when the task I plus 1 is given, then you only see the samples from the gray class and this, how can I say, the blue class, right? And at the task I plus 2, and you only see the samples in the class of yellow and the pinks, right? So given that you can observe online sample in any different mix of classes, we are assuming that these classes are nicely grouped and forming a task and update the model, which I believe this is not very realistic. And people call this setup as a disjoint subset. Okay, so here we slash the time steps and given these tasks as a group and just try to update the model. And on this setup, there are many different methods are proposed, like ICAR and artwork, the random work, and BIC, and Lucier and PotNet, and there are many different papers are proposing a method on this setup. And also, they are assuming that they can update the model in many epochs, so that you can learn the knowledge pretty thoroughly when the task is given. But when you think about the scenarios that the online samples are given to the model, you don't have a luxury to update the model many times over and over again by looking at this batch of samples in many times, right? So the offline learning is also kind of unrealistic when you're thinking of updating the model when the samples are given in a streamed manner, right? And also some of the papers are assuming that you know the Oracle task ID. So when you get this samples from this red class, then you know that, this sample is coming from the task something, task I. So then you can narrow down your search space by either yellow class or the purple class, which narrow down your search space significantly, so makes your problem much more easier. But at the same time, it is unrealistic to assume that you know that this the sample for the inference knows the sample from inference is known. Uh, their classes are known in advance when the inference are happening, right? So this setup is also very unrealistic. And on this setup, there are many different methods are proposed, like GEM and AGEM and TinyER, things like that. And this setup is argued that is problematic by the Prabhu et al. In a paper called Genome in 2020 in ECCB, oral paper, and it's a very famous paper. And we also try to argue that this setup is very unrealistic. The disjoint and offline learning setup is very unrealistic. And we also figure out that this is a real, e-commerce product search record of a Korean e-commerce website called Naver. And the Naver is a search engine, and they also have an e-commerce part, and they have this data for searching the products seasonally, right? So this is a swimming suit and mask and pepero, which is a snack, and padding jumper during the period of November 19th to November, I guess it's October 20th. So you see there are, up and down, curve of searching these products over and over again. So when you think that these searches are given for, this search encourages the uploading the more products for that categories, like swimming suits, then there are more number of data, so like more data is injected to your system, so you have to process them. Either it's recognized or or the recommended to the users, right? So you have to process these inputs. So then maybe you can update your model in a streamed manner by these inputs that is periodically up and downs over times, right? So this joint setup is very unrealistic, and as you all know, and this is one of the examples for that. So as this Genome paper argues that we also, advocate this blurry continual learning setup. I'm gonna explain what the blurry means here. Blurry continual learning setup is very realistic. So the blurry continual learning setup is assuming these tasks are given in this manner. So as the time goes by, the previous task and the current task, you can observe many classes over and over again, but their distribution will be different. Okay. So to compare the disjoint and blurry setup, you can see this is the task setup that you can observe at the task 1, and this is the classes that you can observe in task 2 and 3. And you see many different classes samples at different time steps. Okay, so the dog and cats are dominant, but a car and bike, cow and sheep are also observed in the task 1 and task 2. You can observe many cars and bikes, but you can still observe sorry, dog and cats and cow and sheep, right? And same here. So you can still observe many different classes, but there are some dominant classes and less dominant classes in each time. That's the blurry. But if you are doing the disjoint, then you can observe dog and cat only, and no car, bike, cow, and sheep samples are there in the task 1. I guess you understand what the blurry and the disjoint tasks are. So here are the classification of the literatures. We already shown you the classification of this thing in these pictures, right? So here there are many methods for this setup, and there are many methods for this setup. So this table is summarize everything. And the EWC and ICAR and random walk and GSS and BIC and GDOMs are assuming that we are doing the online learning or offline learning, or they are assuming that they're evaluating their method on the disjoint setup or the blurry setup, and they also assume that we can use the episodic memory or not, or we can use the knowledge preservation by the regularizing the previously learned parameters, or using the knowledge distillation from the previously learned parameters to the newly learned parameters, right? So here we're going to propose a new method called rainbow memory, which we abbreviate by RM. And we assume that they are online and disjoint and blurry and memory setup, and that is very similar to the GDOM, but different from the other unrealistic setups. And also, we are not using any regularization or distillation methods like GDOM. So here, I summarize all the setups that we just argue that this is more realistic, the disjoint and blurry, and we argue that the blurry is much more realistic. And online versus offline, we also argue that the online setup is much more realistic than the offline setup. Yeah, so let me introduce the GDOM first to motivate us why we try to propose a new methods, because GDOM is already very good. Okay, so the GDOM is a simple and unifying approach based on their argument by the Prabhu. The GDOM is abbreviated by the greedy balancing sampler plus the DOM learner. The greedy balancing sampler is basically greedily store samples in the memory randomly, but they try to keep the balance between the samples across the classes. So this greedy balancing sampler is basically a random sampler, but they try to keep the balance between the classes. So it's having like same number of samples per classes are stored in the episodic memory. And the dumb learner is when asked to train a model from the scratch only using current memory samples. So they are trying to update their model once on the new samples. And they combines prediction with the oracle task information via binary mask at the inference. So they also have a oracle task information, which is a little bit unrealistic, but they're using this dumb learner to get kind of good baselines for this blurry and online continual learning setup. And we thought that we probably can do better than this greedy sampler, the random sampler, right? Because, I mean, in a very intuitive glance, the greedy sampler is not going to be the optimal one, right? So we can do better than the greedy random sampling for the episodic memory, for improving the continual learning classifiers. So our idea is to diversify data in the episodic memory, and we call it the rainbow memory. And to do that, we select representative samples, representative in terms of the classification boundaries. And this few representative samples can save the space and to increase the efficiency of the stored information in a very limited budget of episodic memory. And then I made a mistake here. So to choose these representative memory, we have to have some scoring function, which samples are more representative and which one is not. So to get this score, we use the uncertainty of a sample versus a transformation of images on the classifications output. So when we have the sample of X, we try to do multiple different transformations that we are usually used for the data augmentations, and try to pass this as an input to the network and measure how much of this class confidence of this guy. So let's say this X is belong to the class of car. Then we know that this is a car sample. Then we are looking at the confidence of a car class of this sample by transforming this by transformation 1, 2 through n. And by looking at these the confidence of each of differently transformed sample of car, then we measure the uncertainty by the counting the number of majority vote of prediction of the perturbed image by looking at the confidence and looking at the other classes confidence, whether this is still classified as a car or not. And we just count the number of majority voting of correct classification, and divided by the number of perturbations, right? And that we define the uncertainty of the samples. And we select a few of the sample by this uncertainty scoring function. So we first compute all of the sample score. Then we so let's say we have a budget of 100 sample. Then for the episodic memory, then for the class 1, we are getting so let's say we have 10 classes, then we have a 100 sample budget, then we can sample 10 samples for each of the classes. Then we have to sample 10 samples in each of the class. Then we first scoring them. Then we uniformly sample by the uniform stride, so that we can get like very well distributed samples by the nice scoring functions. And also we further propose to use data augmentation when you're using the samples in an episodic memory to make the diversity much more fruitful when you're training when you're training with the newly coming samples for the updated models. So for the data augmentation, we consider the auto-aug and the cut mix or other different augmentation method to make the diversified sample in an episodic memory to be more effective when you're updating the memories. That's it. So by these two simple ideas, we try to improve the baseline performance over the Genome on the Blurry online setup. So our experimental setup is usually using the Blurry setup, and each task has a major class and minor classes. So the major classes are the classes that has more samples, the dominant samples, and the minor classes are not otherwise. And the Blurry 10 means on CFAR 10 with the 5 tasks is basically the 90% of the class 1 and 2 and the 10% of the others. So that is called the Blurry 10. So the overlapping ratio is 10. So the other minor classes are always 10, right? So that's the Blurry 10. So if you say a Blurry M, then you're having the minor classes of the M%. So each task can share the classes, but do not share the samples except for the episodic memory. And our default setup is Blurry 10 and online for many different image data sets, like MNIST, CFAR 10, CFAR 100, and ImageNet. And we all divide them by 5 tasks with memory size of 500, 2,000, and 20,000 based on the size of the entire data sets. And we use the backbone network by these different network because the data sets are all different. Okay, so comparing with the state-of-the-art methods on various data sets, we compare our method with EWC, random walk, and ICAR, and Genome and BIC, and on MNIST and CFAR 100 and ImageNet 1000. We also compare with the rainbow memory without the data augmentation, and also the data augmentation is involved. And by looking at this chart, you can see the proposed rainbow memories are outperforming all of the other state-of-the-art by quite a large margin when the data set becomes larger. Okay. And this star indicates the reproduction of the BIC with only using the classification laws without distilling laws to be better suited for the Blurry 10 setup. So when we are using the distillation laws, then the performance drops much more on the BIC on Blurry setup because the BIC does not consider the Blurry setup at the beginning. So they assume the disjoint setup when the BIC was proposed. So we try to modify the BIC for better suited for the Blurry setup, and this is the best reproduction that we can get by tweaking this BIC a little bit. All right. And on different Blurry portion, we can also evaluate our method versus the other methods. So here we are also evaluate our method on disjoint setup and Blurry 10 and Blurry 30. And as you see in the chart, you can see the rainbow memory is outperforming all of the other methods, except the offline setup, the ICAR or EWC or the RWork is outperforming ours, but the gap is not that much. And here the gap is pretty big, but the other bigger, more difficult setups, or more realistic setup, our methods are more having better performance gap in the online, but is similar, comparable performance in the offline setup. So that is the observation that we can see. And also with different augmentation method, because the augmentation method is a part of our method, but it's not the components of the method. So we can test the cut mix or random aug or auto aug or the cut mix plus the auto aug, and we observe that the auto aug itself is showing the best performance among the others compared to the other state of the art when we are applying the same method to all of the other methods. Okay, so that's the different augmentation methods. And finally, we try to, evaluate our, or we try to validate our uncertainty-based sampling methods amongst the other sampling methods, the random or reservoir and prototype methods. And as you can see in the table, the uncertainty-based sampling method is having a big gap, a big gain over the other sampling methods. But note that this random sampling is not the balanced random sampling. So here is just uniformly random sampling. So it's different from the balanced random sampling that the GDOM is using. And later we're gonna also compare this balanced random sampling in our GitHub repo to give you a more complete picture of uh, comparison of the uncertainty, sorry, the sampling methods of the episodic memory. But this is a note. Right. To summarize, we try to tackle the disjoint setup on continual learning and analyze the various setup like the blurry or the online training. And we propose a memory management using data uncertainty. And also we show the data augmentation is significantly improves the performance in online blurry continual learning setup. And we have released our code in this GitHub repo, so you can just download and try to reproduce our result uh, on the GitHub repo that is implemented in PyTorch. And one thing to note that some may argue that this blurry setup is maybe unrealistically too easy, or maybe this is more realistic but is easier than the disjoint setup in terms of catastrophic forgetting. And I agree. And we agree that this disjoint setup is much more difficult in terms of the catastrophic forgetting because you don't share the class information between the classes, between the tasks. So that's why the catastrophic forgetting may be happening much more seriously in the disjoint setup. But we argue that even though disjoint setup is having much more difficult, the catastrophic forgetting is overly unrealistic because we don't need to tackle that kind of scenarios when the real world data is given not in a disjoint manner. So that is our argument. Okay, so if you have any question, please stop me here and ask me a question on the rainbow memory. And one side note is when we are naming our method as rainbow memory, we also try to keep in mind that the abbreviation is also quite catchy. And this RM is a leader of BTS, if you remember it. So the BTS is a very famous Korean boy band. So we try to make this name more catchy.
Um,
So call
I
it. Yeah, go ahead, James.
was gonna ask, are you presenting more after this one?
Yeah, I'm presenting two more, but it's very
Okay,
briefly. So the
okay.
RM is the.
I was just wondering, question timing. I do have one while you're on here. If anybody
Oh,
else has a question, please feel free to unmute or ask in the chat.
please.
Um, I think sometimes people are afraid to look at data
Right,
augmentations in
right.
continual learning since they think it should improve all methods. But I'm not sure if that's true. I'm wondering, I think some augmentations might be more efficient for continual learning compared to
Right.
how they're leveraged in other methods. And I think you did a
Right.
good job at comparing the different, some different common ones and showing how they affected not just your method, but the other methods in a different slide. So I thought that was great. I was just wondering, I
Yeah.
didn't really have time to look too close at those, but do you have any insights onto whether some continual learning methods benefit more or less from augmentations? Like, for example,
So
what
mhm.
a parameter regularization method better or worse than like a replay-based method?
That's a great question. So we didn't compare the efficiency or the effectiveness of the data augmentation method versus the other very different paradigms like the regularizations or the network expands or something. But we try to compare the augmentation effectiveness on different methods, but they're all rehearsal-based methods. So it's like a subset of what you're asking.
Right, but like on this, now I'm looking closer. Like for example, R walk underperforms EWC with no augmentations in your results. They're pretty close, but then it slightly
Augmentation.
overperforms depending on the augmentation. So I think that's a
Exactly.
very interesting finding you have. Um,
Exactly. And one thing to note, we later found that this auto augmentation requires a policy, right? Policy learned, which kinds of augmentation sequence should be applied to get the optimal, what they're asking, what they're claiming, the optimal policy of the augmentation. And to learn the policy, we may access the entire data set to get the policy in advance. So that may be a cheating. So we try to also fix that when we are making this RM much more practical. Later figured out, but we use the same policy for each of the every method. So I think this comparison is still valid, but
Yeah.
the problem is the augmentation policy can be learned in advance in different external source. That may be a something to note to use the augmentation methods. And I think the auto augmentation is learning the policy on the data. So I think it's kind of close to the optimal. And we are not sure why this conmix plus auto augmentation is outperforming the auto augmentation alone in certain data sets. But still,
Yeah, that wasn't your main point of the paper. That's an interesting thing that someone else can look at in the future, whether it's
right,
you or
exactly.
yeah.
Exactly. So we are not saying that our method, our combination is the best. We are just proposing that we have to diversify sample in an episodic memory, and one of the way is just using the uncertainty and the data augmentation, but not the only way. So you can propose the other method, like and naming is rainbow memory version 2 and something. Yeah. So that's the summary. And we also figured out this blurry setup is also a little bit unrealistic because it cannot see a new task over the task. Okay? So here, when you're seeing this blurry setup configuration, we have a major class and a minor class, right? So we have this dog and cat, but still you can see the car and bike and cow ship, right? At the second task, you're seeing the car, bike major, but in the dog, cat, cow, and sheep are also can be observed. But we believe that this is not very realistic because sometimes you may introduce a new class, completely new class over the task. So we propose a new setup called iBlurry, which is an abbreviation of the incremental blurry, so that you have some portion of disjoint classes and some portion of blurry classes, so that you can have new classes introduced over time in the task, but some of the classes are going to be observed or the shares across the task. So that's why we call this is a blurry blurry portion, and this is a disjoint portion, and we name it as iBlurry N and M. So here the N is the portion of the classes into the disjoint setup, and the rest part is just shared by the M%, like the same as the blurry M setup. So we name it as iBlurry and M setup. And to tackle this problem, we propose a very simple baseline. We name it as clip. And this is basically using the sample-wise importance sampling. So it's similar to some scoring function that we are using the uncertainty-based method, but here we are using the distance from, we are using the loss deviation when the samples are given as given to the network as an inference, and we use this loss deviations for each of the sample and get it as a scoring function, and also doing the same stride sampling for each different classes with the same number of sample to be stored in an episodic memory. So here we replace the uncertainty-based scoring function into the sample-wise importance sampling across the loss function deviation. And once we have it, then we just train the network and do the inference, and that's it. So it's much more simpler version of the rainbow memory, but still keeping the diversity by this sample-wise importance sampling. So we sample memory management by minimizing the loss decreasing samples. So the loss decreasing is now the scoring function, and we sample it by the uniform stride. And we also now using the memory only training. So when the new samples comes and we are doing this memory management, we just compute the loss decreasing. And even though when the new sample is coming, but this new sample is not contributing the loss decreasing much, then we are discarding. So we are not even the newly come samples and putting into the memory. And once the memory is updated, then we just train with the only memory. And also we use the adaptive learning rate scheduling to maximize the performance. I mean, to boost the performance a little bit. And also we further argue that the current continual learning methods are only evaluated at the end of the task, right? So for example, this is a rainbow memory. And when the tasks are given, then we know that the tasks are given, but they're blurry, even though they are blurry setup, the tasks are given and they're updating online manner. And at the end of the tasks are given, then the updates are happening with the episodic memory significantly. So here, when the task is finished, task is given finished, the one task is given completely, then the model is updated fully. And when the samples are given in a streamed manner, the models are never updated. They're updated, but it's very incrementally. So we figured out that this accuracy shoot up at the end of the task is not very realistic, because when you're updating your model continually, then you better assume that the users are asking query, or users are putting the query to the incrementally updating model at any time, right? But here we are only updating the model at the end of the task. So, and also we assume that we know the end of the task, which is kind of unrealistic, because in the real world setup, there is no notion of task, right? So here we think that this is kind of unrealistic as well. So instead of just computing the accuracy at the end of the task and average them, and in the literature, people just evaluate it by the A average, the accuracy average. Instead, we are proposing that we have to evaluate the model at any time, and we have to compute the accuracy over time, so when the new samples are coming in. So we just define a new measure called accuracy area under the curve. So in the case of rainbow memory, the A average is 61%, but the AAUC is very low. But when you're using our new methods on the same task, the A average is 73%, and AAUC is still very similar to the A average, which is pretty desirable properties when the model is getting the inquiry at any times. So we call this as a anytime inference. So we have to tackle the anytime inference by evaluating your method at every moment, and by computing the AAUC. So the simple baseline of this clip on this iBlurry NM setup on the anytime inference metric, we also compute the A average metric. The A average metric is one of the most widely used metric with the A last accuracy, right? So A average is much more difficult, because you have to be better at every end of the task. So we only compare with the AAUC and A average, and it outperformed the baseline, outperformed all the other state of the art on this new, more realistic continual learning setup, by comparing the EWC++ using the episodic memory and BIC, ERMR and GDOM and rainbow memory in our own baseline. And also we make this little bit of minor improvement over the ER, and we call it baseline ER. And finally, the proposed clip method. And by looking at the numbers, we observe that this simple baseline outperforms all of the baselines, all of the other state-of-the-art in both AAUC and A average measures. And this is upper bound when you're joint training. Okay, so you see, even though we claim that this baseline is outperforming the state-of-the-art methods on, like, proposed on the different setup, like a disjoint or the blurry, right? Here is iBlurry, so it's kind of obvious that our method is much more suitably tuned for the iBlurry setup. But the gap to the joint training is still large, so there are big room to improve. So I encourage the future research on this iBlurry setup and the AAUC measure to be much more popularly used. So I think it's better in showing the graph, because the AAUC or the anytime inference is better shown in the graph of the accuracy at all the samples are coming in. So here the blue curve is indicating the clip's performance, and ER is our own baseline, the ER's improvement, the minor improvement, and EWC++ is the EWC with the episodic memory, and the BIC, GDOM, and rainbow memory. And all of the other methods are suffering from the bad accuracy over time, but this clip is maintaining a good accuracy over time when the new samples are coming in a continuous manner. So we also investigate different NM setup. So when you're using the blurry n equals 0, then it's completely blurry. And this is n equal 50 and I blurry, and n equal 100, then it's disjoint. Right? And when you're varying the m, when we're fixing the n, I think we have to fix the varying m, we use n equal 50, and when varying n, we are using the fixed m equal 10. Okay, so here when we are varying n, we are using the m equal 10, and when we are varying m, when we are so we are fixing n equal 50. So in various m setup, we are showing that our simple baseline outperformed the other state-of-the-art, except this fact that the disjoint setup, the BIC, outperforms ours in a very marginal gap in AAUC and A average. Okay. Yeah, BIC rocks still, but in a disjoint setup only. So overall, the blurry and I blurry is, and the simple baseline is actually outperforming the others. Okay, so we also evaluated our model with the different sample important sampling methods. We're using the uniform random and also memory only training, and also adaptive RL schedule, the learning rate schedule. And these are adding up a little bit of gap, but most of the gap is coming from the sample importance memory sampling method. So we argue that this diversifying the samples in the episodic memory is an important thing in the continual learning, realistic continual learning setup. Okay, to summarize, the blurry setup never introduces a new class, so we propose a new blurry setup with a newly entered class and name it as iBlurry. And we propose a very simple baseline to address this, and nothing very new. And this method is not particularly designed for the iBlurry. So we just tune it for the iBlurry, but it's not particularly specific for any iBlurry setup. So you can think about a better method for this setup. So this paper is basically just proposing a new setup, not a new methods. So we propose a iBlurry, and we argue that we have to evaluate the method in all time, which we name it as anytime inference. So please use the AAUC measure much more widely. One caveat of using this AAUC measure is it takes a lot of time to inference because every time you have to inference the things, so it takes a lot of time to evaluate. So that's one caveat. All right, so in the last thing, we all assume that these stream data has no wrong label. So all of the labels are credible. So that's the assumption that we use in the continual learning setup. But this is, all unrealistic, because this online continual learning is kind of very useful when you're using this newly coming samples are annotated by the human labeler. And this human labeler should make mistakes. So we assume that this stream data should have some wrong label. So in that case, how we can tackle this problems? We still keep the philosophy of diversifying the samples in episodic memory, but at the same time, when you're having the wrong label, you're believing this wrong label to diversify a sample, then you're basically diversifying in the wrong directions. So here we divide the coming newly coming samples in an online stream by 3 different partitions. One is C. The C is very credible samples. So we know that, okay, these samples are, so we can trust the samples label by looking at the confidence of this sample versus the given label, right? So the given ground truth label is having a very high confidence on this sample given the previously learned model. Then we assume that this label is credible. And the other 2 partition, we name it R and U, is for the uncertain labels. So we have the samples of X, then we use it as we use for the inference for the previously learned or the currently learned model, and check the confidence, and the confidence is like below some threshold. Then we are saying, okay, this sample's label is not credible. But here we are dividing further by R and U, and R is, yeah, we may use this sample's pseudo label by the currently learned model, and then the pseudo label can be trustable in the updating the model. And U is, yeah, we cannot even use the pseudo label as a credible one. So this very uncertain label is not going to be used, so that we are using these sample by the unsupervised manner. So we are using the samples with some noisy label by partitioning them by the very credible label and middle credible label. Then we are using, so if the label is very credible, then we believe the given label as a true label. And the second, if the given label is not credible, but the pseudo label is very confident, then we are using the pseudo label as a true label for the sample. And if the samples are otherwise, then the ground truth label is not credible, and also the pseudo labels are quite not reliable. Like the confidence entropies are all uniform, it's very high. Then in that case, we just not using the label at all, and we just use these sample as in a unsupervised manner to update the model. We are not discarding any samples, but we are using it in an unsupervised manner. So by the simple method, we get this new method called PuriDiver, which means that the purifying the samples by this credible labels and the diversifying the episodic memory. So we name it as a PuriDiver. It's like a LG purifiers, the water purifier. We are not coming from LG, but yeah, we name it as a PuriDiver. So by using this simple technique, we observe that this is a noisy label portion and symmetric noisy label portion, and this is a asymmetric noisy label portion. When the noisy label portions are increased, then the performance gap to the state of the art with different robust learning methods combined to the previous methods. So we combine the robust learning methods that purifies the labels to the previous state of the art to RSV, which is RSV and GBS and RM. So we use the selfie or co-teaching or divide mix robust learning method to purify the labels to these continual learning method. But the combination of these state-of-the-art purification and the continual learning method is less performing than the joint manner training of PuriDiver on the different noisy labels of the symmetric and asymmetric labels. And we use here, I didn't specify, I think this is this joint setup or the blurry setup, I'm not so sure, but you can see in the paper whether this is a blurry setup or the this joint setup. And on this setup that we observe that this simple PuriDiver baseline is performing the other state of the art. Okay, so not this much on the the PuriDiver because this is not yet published, but you will get the sense what it means. And I already put the sorry, the archive version in our paper in our website, so you can take a look at it. And I mean, actually, I try to make it short because of the running out of the time. So it's not just try to hide the details. So you can take the details in the papers if you're curious about the PuriDiver setup. And so here, across all three papers, we try to argue that this sample diversity in the episodic memory is play a pretty important role in continual learning, either in the blurry setup or the disjoint setup. But we still argue that the blurry setup is much more realistic. So we encourage people to use this more realistic setup to make the method more practical. All right. So in this PuriDiver, we summarize that the sample diversity is still important, but needs to be reconsidered, because if you try to diversify the sample with their label, then you're basically make a wrong diversity, putting the wrong diversity in the episodic memory. So to address this, sorry, to address this problem, we partition the label samples by three sets and treat them in different manner to implement the truly diverse samples in the episodic memory. And the code is available here, so you can download and reproduce. All right, so the key takeaways are following. The episodic memory management policy needs to be reviewed, like rainbow memory and Puri Diver or iBlurry. We argue that the episodic memory should be containing the diverse set of samples to keeping the information of the past task much more fruitfully. And the Blurry setup needs to be reviewed. So the iBlurry is also more realistic, we argued. So in some, we try to argue that we need to monitor whether the literature is moving the right direction or not. So if you think that the setup is unrealistic or not just agnostically try to improve the numbers in a given setup, we have to rethink that the setup is actually practically useful or not. So the scenarios we take granted may not be very realistic, so I urge the researchers in this field to rethink about the setup that we are actually try to improve the number by proposing a new components. Okay, so for more details, please visit our group page or my personal page for the paper access and the code access link. And if you have any question, please email me at this email address. And I really thank you to my amazing collaborators across these different organizations and Naver AI Labs and just the previous application and the UNIST, which is another tech school in South Korea, and the Seoul National University and Microsoft Research. Right? Thank you. I'm happy to take any questions here.
I noticed, Elaine, I think you had a question earlier. If you want to ask
please.
that.
Oh, I would just want to ask about the first paper, like rainbow memory,
Okay.
like how you construct the blurry samples, like how you just randomly pick 10 or 30 or something like that.
Oh, so when we are making this blurry split, we say the blurry split, we construct the task one, task two. So each of the tasks has a major class and a minor class. The major class is the classes that has the most of the sample on that task. So in the task one, we have 90% of the samples are coming from class 1 and 2, and 10% of the sample is coming from rest of the classes. If it is CFAR 10, then 10% of the samples are coming from class 3 to 10. And the task 2, we specify the major class as class 3 and 4. So the 90% of the sample is coming from the class 3 and 4, and 10% of the samples are coming from the class 1, 2, and 5 to 10. So that's the setup. So here, when we are getting the sample, then we are, getting the uniform sampling, and we make this random sample or random split publicly available. So you have to download this sample task setup to get the same evaluations. So we have an image ID there, basically. Oops. Yeah. Does it sufficient? Is it sufficient?
Yeah.
Am I answering the question?
Yeah.
Thank you. So any other questions?
I have one more. Oh, Elaine, you
Go
please go.
I go. Okay. So, since the last paper is kind of tackle problems with like noise label, so is it possible to apply in a setup like a semi-supervised learning, like without label, like some samples without label?
That is true. That's a good point. So here we can also formulate our problem as a semi-supervised learning at the task transitions.
Yeah.
Here, some of the labels, some of the sample has a label and some of the sample doesn't have a label. But we also try to move on that direction. But at the same time, we figured out that this noisy setup, the period diver methods, we regard some of the samples are unlabeled, right? So here
Yes.
we are basically using the semi-supervised learning technique by partitioning the coming samples by C, R, and U partitions. And if the samples are falling into the U categories, we are not using their labels, and we just use this as we just use this sample as a semi-supervised manner.
Okay.
So this PureDiver paper, you can see the method. This PureDiver method is also using the semi-supervised learning technique inside. So this is kind of a general method to tackle this unsupervised samples too. And there is one iClear paper also happened to be coming from South Korean group that the continual learning on the unlabeled samples. So they try to do the representation learning on the samples that is coming in the streamed manner. So it was iClear oral paper this year. So that's also kind of useful for you to read once. Yep. So any other questions?
My question was a little open-ended, so for time's sakes, I can cut it out right now, maybe ask you offline.
Sure.
But if there aren't any other questions, I guess we can go ahead and wrap things up.
Mm-hmm.
I want to thank everyone for joining today, especially thank you, Changyoon, for the wonderful presentation covering all of your work, or all of this work, I should say. I want to make a note now if anyone's interested in joining Continual AI organization as a full member. You can visit the link that's posted in both the description of this video and in the live chat on YouTube, and you find out more there. You can catch us again next week. We'll be back at our regular time at 15:30 p.m. UTC, 17:30 Central European Summer Time, and we will be hearing a presentation from Diganta Misra on the work Anytime Progressive Pruning. So I'm looking forward to that, and I guess I'll see everybody next week. Thank you again for the presentation.
Thank you.